Hello, students. Have you ever thought about this? Can an object have energy even when it is perfectly still? Well, today we're going to learn about a very fascinating type of energy, an energy that's stored in things even when they are not moving. Let's begin our journey into the world of potential energy. So, before we start, let's have a quick look at the roadmap for our lesson today. First, we'll see some examples of stored energy all around us. Then, we will understand what potential energy actually is and how to calculate it. After that, we will see how this energy changes its form, and finally, we will solve some problems together. It's going to be a very interesting session. Okay, so let's get started with our first section. We are going to look at some very familiar examples of stored energy, and you will see that it's actually quite common in our day-to-day lives. Let's come back to that question I asked at the beginning. Can an object have energy when it is not moving at all? We generally think of energy as something that causes motion, isn't it? But what about a book that's just lying on a shelf? Does it have any energy? Let's find out. Look at this picture of a bow and arrow. The bow is stretched, but right now, nothing is moving. But you know, don't you, that if the string is released, the arrow will fly off with great speed. Why does that happen? It's because the work that was done to stretch the bow is now stored inside it as energy, an energy that is just waiting to be released. And this idea of stored energy, it's really everywhere. Think about it. A stretched rubber band has the potential to snap. A wound-up toy car has the potential to start moving. A hammer that is raised up has the potential to drive a nail into wood. And the water stored high up behind a dam has the potential to flow down and generate electricity. In all of these cases, work was done on the object, and that energy is now stored inside it. So, this special kind of stored energy, what do we call it? Well, in physics, we have a very specific name for it. We call it potential energy. So, let's understand the definition. Potential energy is the energy that an object has because of its position, like its height, or its configuration, which simply means its shape. Think of it as energy that is stored and has the potential to do work later on. It's all about where an object is or how its shape has been changed. Now, there are different types of potential energy. The energy in a stretched rubber band or a compressed spring is what we call elastic potential energy. But for today's lesson, we are going to focus on the other type, gravitational potential energy. And this is the energy an object has just because of its height above the ground. So now we know what gravitational potential energy is. But how can we measure it? How can we give it a value, a number? Let's see how we can calculate it. I want you to think about lifting your school bag from the floor. You have to apply a force with your muscles to lift it up, isn't it? When you do that, you are actually doing work against the force of gravity, which is always trying to pull a bag down towards the center of the Earth. We can actually find the formula for this energy using what we have already learned about work. Do you remember that work done is equal to force multiplied by displacement? Now, to lift an object, the minimum force you need is equal to its weight, and weight is just its mass, m, times the acceleration due to gravity, g. The displacement here is simply the vertical height, h, that you lift it to. And here is the most interesting part. The work that you did to lift that object does not get lost. It gets stored inside the object as gravitational potential energy. So the formula becomes very simple. Potential energy, which we write as E with a small p, is equal to m times g times h. EP equals mgh. The energy stored is exactly equal to the work done. But wait, a small doubt might come to your mind. When we say height, H-I-G-H-T, height from where exactly? From the floor? From the desk you are sitting at? From the ground outside your house? This is a very, very important question to ask. You see, the important thing to remember is that potential energy is relative. It means we have to choose a starting point, a zero level or ground level for our measurement. For example, if you are on the first floor of a building, your height is different if you measure it from the ground floor compared to if you measure it from the basement. So for most of our problems, just to keep things simple, we will take the ground as our zero level. All right, so what happens to all this stored potential energy? If you lift a book and then you let it go, does that energy just vanish? Let's find out what happens when this potential energy is released. Well, the energy does not just disappear, it simply changes its form. This is one of the most important and fundamental laws in all of physics. It is called the law of conservation of energy. It tells us that energy can never be created and it can never be destroyed. It can only be transformed from one form to another The total amount of energy always remains the same. Let's understand this with the help of this falling ball. At the very top, just before it is dropped, it has the maximum potential energy because of its height. It is not moving, so its kinetic energy, the energy of motion, is 0. Now, as the ball starts to fall, it gains speed. Its potential energy starts converting into kinetic energy. And just a moment before it hits the ground, its height is almost 0, so its potential energy is minimum. But its speed is maximum, which means its kinetic energy is maximum. You see, the energy just changed its form from potential to kinetic.
Okay, now that we understand the concepts, let's try to apply our knowledge. We are going to solve a couple of numerical problems, the kind you might see in your exams. This will help us see how the formula works in practice.
Let's solve this first problem together, step by step. The question is, find the energy of an object of mass 10 kilograms at a height of 6 meters. First, we write down what is given to us. Mass, m, is 10 kilograms, height, h, is 6 meters, and g is 9.8. Next, we select our formula, EP equals mgh. Now, we simply substitute the values, 10 multiplied by 9.8 multiplied by 6. If you calculate that, the answer is 588. And what is the unit? Joules. Always remember to write the units. Very good. All right, shall we try one more? This one is slightly different. Here, we are given the potential energy and the mass, and we need to find the height. We start with the same formula, EP equals mgh. But this time, we need to find h. So we must rearrange the formula a little bit. H will be equal to EP divided by m times g. Now we can put in the values. 480 divided by, in brackets, 12 multiplied by 10. That is 480 divided by 120. And so the final answer is 4 meters. Excellent work. Wonderful. You have all done very well. Let's do a quick recap of everything we have learned today, just to make sure we remember all the important points. So here are the 3 main things to take away from today's lesson. First, potential energy is stored energy. Second, the formula for gravitational potential energy is EP equals mgh. And third, a very important point, energy is never lost, it just transforms from one form to another. Please keep these points in mind as they will be the foundation for what we learn next. And this leads us to a final, very big question to think about. If the total energy in a system, the sum of potential and kinetic, is always constant, what does that tell us about our universe? This is a very profound idea, and it leads us directly to the law of conservation of mechanical energy, which we will study in our next explainer. Thank you for your attention, and I will see you next time.